is talk a little bit about essentially the digital image, okay, and how we can measure in some way something which we can frame as a measure of the quality of an image. Okay, it's a bit of a subjective, I guess, terminology, but there are some objective ways in which we can analyze an image and the information in it that can give us some information on what we can define as quality, but at least, maybe not absolutely, but at least we can compare different images, different imaging systems, and the images that they produce. So a lot of this will hopefully be quite familiar to you. We're going to focus on medical images, but we're all surrounded by images every day. We're taking them every day with our smartphones, and a lot of the concepts that apply to optical images also apply to medical images acquired using different modalities. Okay. So the pixelated image, the concept of the dynamic range and bit depth. I'll talk a bit about contrast in images, noise, spatial resolution, and finish off with a bit about the modulation transfer function. So I'm sure you're all aware that actually an image is a digital representation of some real object. Okay, and that's important to remember. It is just a representation through some sort of measurement. Okay, and that means it's not going to be exact. It's not going to necessarily be an accurate or true representation. It is purely just, in some way, representing the real object. And this CT slice is a good example. Okay, we tend to look at it and sort of take it for granted that this is actually how anatomy really looks inside someone. Okay, but if we look at it in more detail, we do actually realize that it is just a sampled representation of what's really going on in the patient. Okay, because if we zoom in on a little section we can see here, we can clearly see that it's not a continuous representation of the anatomy in that patient. It's actually individual pixels, as we call them, and each pixel has an individual grayscale. And if we zoom in on those, well, we start to lose some of the information there. I mean, that just looks, if you just saw that insert on its own, okay, if we just looked at this and weren't told anything else, you'd probably struggle to guess what it was. But when it's in the context of this CT slice, it's a lot more, it gives us a lot more information. Okay? So this is a 2D image made up of what we call picture elements or pixels. We can extend it to 3 dimensions, and we do this with CT. So we have multiple 2D images. In planes in front and behind this. And we assign each pixel a brightness or grayscale value, as we call it. Okay, we normally would represent CT data, X-ray images in grayscale. But in the case of CT and X-ray imaging radiography, we've got to remember that actually each of these pixel intensities is actually related to a physical quantity, the measurement that's been made. In the case of CT, it's related to the attenuation of the X-rays. So the way it's displayed, bright pixels mean we've had lots of attenuation, so in some ways it's the inverse of what we would expect. Okay, but historically we sort of show images, we invert the images so that high attenuation equals bright pixels. Okay, and it also I guess it's a bit more intuitive to us because in reality bone is actually white, so we can relate to that. We can see that bright, very bright white sort of pixels in this image correspond to potentially bony anatomy. Okay, but that's a scaling issue. It doesn't necessarily have to be bony anatomy. Okay, so it's an attenuation map in this case. So when we store this information in the image, this pixel image, we store it in digital format anyway. We're going to store it in different locations, addresses, if you like, in computer memory. Okay, and these are not necessarily, but the easiest way to imagine it is that these sort of are sequential addresses or locations in memory. Okay, that isn't necessarily always the case, but I think conceptually this is easier. So if we imagine our image is actually, or a 2D image is made up of rows and columns, so as we sort of go across row by row, we can represent this as one continuous sort of list of memory locations. Okay, and that's what this is trying to sort of show. If we imagine computer memory where each of these individual lines represents a location, an address, in digital memory, then the sort of grayscale value of that pixel stored in a location. Okay. So when we actually store it in this way, this is trying to actually represent the different grayscales, I guess. It actually is pretty meaningless. Okay. It's only when we put it together as a 2D array, where everything is in the right place spatially, that it actually makes some sense to us. Okay. So that the pixel value is some can take on any number. Okay. So it could be a continuous variable. So attenuation of X-rays, for example, it can take on any value. It's a continuous variable. But digitally we don't represent it that way. We allocate a particular discrete value to it. Okay. And in the case of the grayscale color, it's a shade of gray. Okay. We can also do it in color, and I'll show an example of that in a minute. Okay. But the number of sort of shades of gray that we use is limited, and it's going to depend on the data type that we're going to use. We need to understand, when we're thinking about images, we need to understand the binary number system, because that's how the information is stored in our memory location. Okay, so actually, that representation that I showed you of memory locations for each pixel, it actually requires more than one memory location for each individual pixel. Okay, unless it's purely a binary image, where the only possibilities are that the pixel value has 0 or 1. Okay, generally, that's not the case. We need more values than that to represent the data. So we need to use more what we call bits per pixel. Okay. So hopefully you're all familiar with the binary number system. We can represent any decimal number in binary, and that's what I've tried to do here for numbers 1 to 15. Okay. So that obviously the digital number 0, binary representation is 0. 1 is 1. It's once we get to 2 and above, we start to, we have to. It's not totally intuitive to us, but it's relatively easy to understand. So once we get up to numbers above 1, we have to start using more than 1 bit per pixel. Okay, and we can continue with 2 bits per pixel to represent numbers up to 4. Okay, and then once we go higher than that, we have to start using a 3rd bit. Okay, so if we had 3, this would require 3 memory locations. So the bit would be set to 1, the second one 0, and the third one would be set to 1 as well. Okay, and up to 15. Okay, if we wanted to go beyond that, we would have to introduce another bit. Okay, so the larger the number, the larger the range of values we need to represent, the more bits we're going to need, and therefore, by definition, the more memory we're going to require to store that image. Okay. So we need to, in terms of grayscale, if an image has what we call a bit depth of 4, or a 4-bit image, we would use 16 shades of grey. Now, the human eye is actually able to distinguish up to about 100. Okay. So generally, when we're storing digital images, we don't really need to use much more than 8 bits. Okay, so if you go through if you go back to that, and if you extend the numbers up to 200 up to 255, you'd find that we need to have 8 bits to represent the largest number, 255. Okay, and this is quite this corresponds to 1 byte, which again is a unit of memory that we use, frequently. Although these days we talk in terms of gigabytes and terabytes. So, and just using 8 bits per pixel, okay, it allows us to have grayscale values between 0 and 255. That's 2 to the power 7. Okay, and so each pixel is going to require 1 byte of memory to store that information. Okay, because there'll be 8 bits, so 1 byte. So the image size that we see on the disk is directly related to the dynamic range and the bit depth. So this range of grayscale values that we have is known as the dynamic range of the image. So, if we go through it, we can work out an 8-bit image. So if we have 256 by 256 pixels, okay, it's going to require 256 by 256 by 1 byte of memory, which comes to 536 bytes, okay, or 65 kilobytes. So a 256 by 256 image using 8 bits per pixel is going to require that amount of memory. Okay, we might need, in some situations, a wider dynamic range. Okay, so for example, 16 bits, we might not need so many pixels. Okay, so you can work out, that's obviously going to be 2 bytes per pixel. 128 by 128 by 2 would tell you the size of that. Okay. Sometimes we need to store numbers that actually have a negative value. We can do that relatively easily in binary as well. We just use the first bit to represent the sign. Okay, and then that then makes available, of course, we can only go up to values of 128, but we can have plus or minus 128. So it actually gives us a range of values between minus 127 and plus 127, which is still the 256 grayscale values. Okay, so when we're dealing with images and we're talking about data types, it's important that if we want to sort of write something that's going to read in the data, it's important that we know the data type, if it's signed or unsigned integers that are being used, because that's going to affect when we read the information in, it's going to affect the conversion from binary to a grayscale value. Okay, because if we try and do it not realizing that first bit is actually representing the sign, it's going to give us an incorrect grayscale value. So the bit depth has a direct consequence on how the image looks to us. Okay, I'll avoid using the word quality. Okay, I'll just say it just has an impact on how the image looks to us. So if we're using the full 8 bits, 256 gray levels, we might have a CT slice that looks something like that. If we drop it back to just using 32 gray levels, you can see we can still represent that CT slice reasonably well. Okay, still got most of the information there. Our eyes don't really pick up the fact that we've reduced the number of grayscale values there. Once we drop it down another bit, okay, to just the 8 gray levels, we can start to see, we can detect that. Okay, we're not able to get the full range of, in this case, we're not able to sort of really see the full range of grayscale required to represent those different attenuation values. Okay, and if we drop it back even further to just the 4 gray levels, you can see it's clearly, it's, the image is not looking the same there. We can clearly see that we're limiting the information we can represent by not using enough bits, okay, to represent the full range of attenuation values there. Okay. It's sometimes an advantage to display images in color. Okay, we're actually, we live in a world where we do see color. Okay, so in some situations, colour allows us to interpret an image more clearly, I guess, with in a clearer way is maybe the best way to describe it. So you spent the first half of this semester looking at sort of functional imaging, nuclear medicine, PET, and we commonly display nuclear medicine data using colour washes, okay, using a colour scale. And that just allows us to clearly visualize the regions where we've got, in the case of nuclear medicine or PET, high uptake. Okay, it's just you know, obviously we can look at that and straight away we can see, you know, we're able to interpret it and see where the hot spots are, if you like. Okay. So how do we actually use this? We can convert any image to any color scale we want. Okay, we just have to have what we call a lookup table that maps the grayscale values to the color scale that we want. Okay. Now, for nuclear medicine images like this, we quite often use this sort of blue is the lower end, red is the upper end, the sort of cold-hot color table. Okay, and we use terminology like that. We talk about hot spots and cold spots in these images. Okay, so you know, there's a psychological element there, I think, where we, you know, when we look at these images, we can visualize straight away that red means there's a lot of activity there, it's hot. Okay, but we don't have to, and there are other situations where different color washes, you know, are a better way to represent it. And it's not just from, you know, we have to think about the sort of psychology of the situation. The CT data was a good one, you know, where we tend to actually, the bright pixels indicates high attenuation. Bone is white. Okay, again, it makes it more intuitive for us to interpret the image. Okay, so we've got the image in memory where we have the sort of list of locations, pixels. The number there is a grayscale value, and what we need to do is just map it to whatever color scale we want. So you can see in this particular image, so we've got, imagine this is an image, the first row, we've got four pixels per row, so we've got 4 7s there, then we've got 2 3s, and you can sort of see how we've mapped the different colors. We've mapped 7 to black in this case. Number 1 has been mapped to red. Okay. What else? And then we've just put where's yellow's on there as well somewhere. Okay. And we can do the same thing. Actually, yellow's not indicated with narrow there, but we can show the same, do the same thing. Okay. And if you sort of go through, you can, with this simple small image with just 3 colors, black, yellow, and red, we can see how the grayscale values have been mapped to that color. Okay. And you know, MATLAB has lots of different color tables available to us that we can use. We just have to tell it which one to do, and it'll automatically map our pixel values to that color table. Now, I've already said it that an image is just a representation. Okay, it's not necessarily a true representation or exact representation. It's some, I guess, sampled representation of the object. Okay, and this means there's going to be some error on the measurement we make. Another important thing to realize is that no 2 images are identical. Okay, and that goes for the images you take with your phone. Okay, they might look identical. You can take an image of exactly the same scene, 2 images, and your eyes look at them and say, yeah, they're identical. But actually, if you were to look at the individual pixel values, okay, you would see that they are quite different. Okay, and that's because there's noise in the imaging process. Okay, there's a random element that is there. Now, smartphone technology, has evolved to a state where we've managed to reduce the noise to very low levels, to levels where you really have to go searching for it to find it. Okay, and then there's lots of software which reduces the effects of noise as well and improves the image quality. Okay. But again, even the latest, Apple have just announced a new smartphone with, I'm sure, an even better camera and software that goes with it. It's still just a representation of any object it takes a picture of. And it's a fair question to ask, how accurately does the image portray the object that we're looking at, we're taking an image of, or some function, in the case of nuclear medicine. Okay, that's what we're imaging, is function rather than anatomy. Okay, so we need to be able to, first of all, understand this, that all images are different, there's noise in the image, and then we want to be able to have a set of tools available to us that allow us to assess image quality, so we can answer this question. Okay, and in medical imaging, it can be very important. It can literally be a matter of life and death. Okay, the quality of the image. If there's something in an image which is misrepresenting some function or some pathology, for that patient, it could literally mean life and death. On your iPhone, I would argue that it's probably not so important. Okay, it might be that you don't look so good as you like in your selfies or whatever, but that's certainly not a life and death. At least it shouldn't be anyway. So we have a scene that we're trying to image, okay, and we acquire an image within it, some sort of imaging system, and that gives us this image gives us a representation of this scene. Okay, so this tries to show. I mean, it's obviously I guess the scene should really be a pathology slice through through the patient, or obviously, or an actual photo, or that would be, even the photograph wouldn't be a true representation of it. Okay, but it's trying to show that we've got the actual anatomy, and then we acquire an image, and that tells us the imaging system has a measurement of that and gives us the representation through the image. Okay, but the imaging system has a transfer function. Okay, it's transferring the real information and converting it into this representation and giving us this representation of that, using the word real information. Okay, and we call this the transfer function or the system response function. Okay, and we need to know this for each pixel, for each location. Potentially, each pixel in our scene has a different transfer function to the map that maps to the image. Okay, now we can simplify this whole concept if we make the following assumptions. Okay, first of all, that the relationship between the scene or the object and the actual image, that relationship is a linear one. Okay, that's the first assumption. The other one is that of shift invariance, and that means that every location, every pixel has the same response function. Okay, that we don't actually have to worry about having a different response function for each location. Okay, and that allows us to simplify the analysis. Okay, so if the linearity assumption allows it to be just formulated as an integral. Okay, our image is going to be an integral of double integral of, because we've got two dimensions here, of the object function multiplied by, in this case, the transfer function. Okay, and we can just represent it in this sort of format as well. Okay, remember it's a two-dimensional. It's each pixel. We still have this XY coordinate in there. Okay, but it's the same transfer function for each pixel effectively. Okay. The shift invariance one means that this response function is not going to change as a function of location. Okay, and this is quite an important one because it means that our integral here becomes what we call a convolution. Okay, it means that this response function that we have is just going to act on each pixel, and a convolution essentially says, well, we're just going to move this response function across the image, and we're going to add up the effects that response function has on each pixel and all the other pixels around it. Okay, so this is quite a powerful assumption to make because it does allow us to represent the image and the response function and the relationship as this mathematical convolution. So in the case of 2D detectors, in MATLAB sort of terminology, we can think of it as a matrix. Okay, it's a two-dimensional matrix of dimensions m by n. Okay, where m and n are integers, and then we have a response function that's going to apply to each pixel. Okay, and one of the features of a convolution is that if we do a Fourier transform, then it just becomes a multiplication. Okay, so this is the first time we've introduced Fourier transforms here, but we're going to learn that Fourier transforms are actually a very powerful tool and concept in image processing. Okay, the reason being that if we can do the Fourier transform into frequency space, then this relationship becomes a simple multiplication, and it means that we can actually start to separate them. Matrix multiplications and divisions are much easier to manage than the convolution in real space. Okay, so we can determine maybe what f is knowing h by doing a Fourier transform. Okay, so this is an important, concept to understand, the fact that we can Fourier transform the response function and the object function, and then it becomes a multiplication to give us the image. Okay. Now, of course, it's complicated by the fact that we have noise in our image. Okay. So this is normally this noise is additional noise, so it just adds to the function. What is the source of this noise? Well, it's the process in which we generate signal carriers in our detector. With a medical image, we're normally detecting quite possibly some ionizing radiation. Okay, and that radiation detector creates charge carriers generally. Okay, and we've seen in radiation physics last semester how that means that there's going to be a resolution effect. The fact that the number of charge carriers that gets produced for a given quanta of energy is going to vary stochastically. Okay, and then the next point is that most imaging systems, the detection of the signal and the production of the output signal is a multi-stage process. Okay, so we might have to detect some electron-hole pairs, for example, and then subsequently we need to collect those, and then that electronic signal is amplified and so on. And each step is going to introduce some noise or some uncertainty into the final signal that we get. Okay, and even the electronics. Okay, we tend to think that electronic signal is just something which propagates through, but it doesn't. Electronics, because we use the term electronics because it involves the propagation of electrons, and that's we know that at that sort of level, quantum noise is going to influence those signals. Okay. Now, for most imaging systems, this noise can be considered Gaussian. Okay, and it's sort of centered on a zero mean, if you like. Okay, but it will have some finite width. So it means that any signal that we measure is going to have a spread of potential values characterized by a Gaussian function. Okay. Another important aspect of the medical imaging process, or the imaging process in general, okay, is the fact the spatial sampling. Okay, we've got if we have an object, it is a continuous distribution of locations. Okay, when we take an image of that object, we can't represent that exactly. Okay, it would require an infinite number of pixels. Okay, so what we have to do is say that, well, we have to accept that each pixel is actually going to represent some small area. Okay, and that's the best we can do. Obviously, the smaller the area represented by each pixel, the better the representation is going to be. Okay, but the larger the image is going to be, and this is something that the digital camera manufacturers have jumped on, is the number of pixels that they have on their digital sensors. Okay, but we passed a long time ago the point where you can actually see these effects with your eyes on a small screen. Okay, unless you're going to be blowing it up into a large format, you're just not going to. That we've got more than sufficient sampling intervals in most digital images these days. Okay, but medical images are a little bit different. So our image is going to be this discrete, sort of sampled spatial representation of the object we're trying to image. And what we're effectively doing is we're taking a point in space, and we're sort of going to say that the value we assign to that point is going to be a sort of average over the area, okay, over some small area around that sampling point. And that's what this is sort of showing there. Each of these is the sort of sampling points, but it sort of represents the value we assign to this point is going to represent an average over this area. And with an X-ray radiograph or a CT, what we're doing is we're dividing the patient up into individual elements, and we're sort of saying, well, we're going to take the average attenuation coefficient over this region. Okay, but we have to remember that. On the detector, the distance between these sampling points is called the sampling pitch. Okay, and we have to remember the detector element. I think in this figure they call it DEL, this detector element. This is sampling a continuous signal. Okay, so again, we can represent this mathematically as in this case, we've got 2 dimensions, so it's a double integral. Okay, so we've got a digital representation of a continuous object, and then this is the sampling function. Okay, and this illustrates the effect of those pixel sizes on our images, or the sampling intervals. Okay, you can clear the first one. We've got 1.5 millimeter pixels on this CT slice. We sort of a factor 2 increase in that. Again, another factor 2 to 6 millimeters, and we can quite clearly now start to see the pixelated nature. Okay, this isn't high enough resolution or sampling interval to really start to see the fine detail in that CT image. Okay, and if we go out to 12 millimeter pixels, then it really we lose a lot of information there. So you can sort of see that the difference between these is not so obvious, and if we were to go to 0.75, we would hardly notice it at all. Okay, on this sort of screen, at this sort of projection size. But it does. We do need to think about this sampling, and there's a theory around it. So what we're doing is we've got this continuous signal. We're trying to represent it with a discrete grid, effectively. Okay, that's effectively the same as multiplying this continuous function by what we call a comb function. Okay, now a comb function is just a long line of delta functions. Okay, so if we take a continuous function and multiply it by a comb function, that gives us the sampled image. Okay, or the sampled version of that signal. Okay, and we can also do this. Remember, multiplication if we sort of switch between Fourier space and real space, or a convolution, becomes a multiplication. Okay, so we can represent. This is the Fourier transform of the continuous function convolved with the comb function is equal to this discrete function here, or the summation. Okay. So the sampling rate can be quite important. Okay, by sampling rate we mean the interval between points. Okay, and this theory, this Nyquist sampling theorem, you maybe have come across it before in signal processing courses. Okay, it tells us what sampling interval we need to use to make sure we capture all the information. Okay, and by that I mean we need to understand that even a representation of a real object, we can actually split that up into its frequency components. Okay, and images are the same. When we look at a scene, okay, I'll call it a scene, what we see is a mixture of low frequency information and high frequency information. Okay, now I'll give you an example of what I mean by this. Is when I look out into the class, okay, I see that there are individual people sat there. Okay, that I would probably call low frequency information. I can, if you just take into account the fact that there are different people there, that's without any worry about, distinguishing the fact that you're individuals. That's what I would call low frequency information. But then if I start to look closer, I start to sort of realize, oh yeah, you look a bit different to the person next to you. That's so-and-so, that's so-and-so. The detail in your faces, your facial features, other small details, that's the high frequency information. So all scenes, objects are made up of this. Okay, and if you've done studied physics, you would have done some mathematics. I'm sure you studied Fourier transform. You know that we can take a function and we can split it up into its frequency components, and we can extract the contribution of those different frequency components. So, different frequencies will have higher magnitudes in a particular object. Okay, and it's the same with imaging. So if we do a Fourier transform of an image, okay, we get the sort of we can get information on the spatial frequencies and how they're represented. Now, the sampling interval actually dictates what the highest frequency is that we can actually get. Okay, so if we display some function, okay, and we don't have a small enough. Remember, we've got to be careful here. Remember that in Fourier space, and when we're switching between the two, it's the opposite. So a small sampling interval, so very closely spaced points in real space are actually broad sort of spaces in frequency space. Okay, but we have to be careful, because if we don't have a high enough sampling interval, then there's a danger that we're going to not include all the spatial frequency information. Okay, so let's say, for example, I was just going to, if I look out in the room and, my eyes are seeing very small, high resolution data. But if I was to just sort of take, sampling points every meter, for example, there's no way I'm going to be able to see the individual high frequency information that tells me about individual people. Okay, and so then there's because in Fourier space what we get is a repeating of this function. Okay, there's a danger that when we repeat it, okay, it's just that there's going to, if we don't have a high enough, or if we don't have a sampling interval high enough, there's going to be a misrepresentation of the high frequency information. It'll be aliased as low frequencies. Okay, and this sort of is going to distort the image that we end up seeing. Okay, and it's what we need to do is we need to this sampling theorem tells us that we need to have a sampling interval, where the sampling interval here is A, so this is the space between pixels, needs to be, this 1 over 2A needs to be greater than the highest spatial frequency in our image, okay, to avoid this aliasing effect. So a sine function is an easiest, very simple way to understand this. Okay, the blue line there is some oscillating signal, and then the points, if we just have here we've got, there's no units on here, but if we have a sampling interval of 5, okay, you can see that to represent this signal, then what's going to happen is, if you know that it is a sine, or a sinusoidal function, we can plot a sine through these points, but the frequency of this is not a true representation of the actual sine signal. Okay? So that's going to cause us problems, because we're going to see this information, we're going to miss the high frequency information that's actually present in this signal. Okay, so aliasing is when a high frequency appears falsely as a lower frequency. Okay, and we get a spurious resolution. The other sort of end of the other side of the coin is we can oversample. Okay, because quite clearly here we've got very small sampling interval. Okay, we get a very good representation of the signal, but it's going to take a lot more memory processing to do that. Okay, so oversampling is equally bad, because we're going to lead to redundant data and just excessive use of computer memory and disk storage capacity. So that's why this Nyquist sampling theory is very important. We need to know what the highest spatial frequencies that we want to measure are, and then choose a sampling interval appropriately. Okay, but I'm sure you've all seen this. Okay, you see it on TV. Someone will be wearing a shirt with very fine lines, and it goes all wavy and blurry. That's this effect. Okay, it's where the frequency information in that shirt, the separation between that shirt, the sampling is the highest frequency in there is going to not meet the Nyquist sampling criteria. Okay, so next time you're watching TV and you see if there's someone who works in TV, they should never wear a shirt like that. They'll know. But quite often you'll get a guest on, coming on, and they don't realize that. No one's told them, or someone's being interviewed on the street. And it just means that the resolution on the camera, the sampling interval on your camera system, is not high enough to capture the high frequency information on that person's shirt. Okay? We get it in medical images as well. You can see it here, where we get these sort of lines running across the image. That's aliasing again. We've got misrepresentation of the frequency information in that image, and it's going to, it can mask important details in the image because we're missing the high frequency information, which can be important sometimes. Okay, so another important measure of image quality is contrast. So it's essentially, it tells us how good we are at distinguishing two objects, okay, and the different intensities in those objects in the images, the pixel values, okay. So you can see what we've got there at the top. There's on the left is what we call a low contrast image, and on the right will be a nice high contrast image, okay. So generally we want to get as high a contrast as possible in our measured image. Okay. So it's essentially the ratio of the signal difference to the average signal. So let's say, for example, we've got some different, the simplest way to define this is we have an object and inserted in it. So imagine this is soft tissue or water equivalent. We have an insert, which could be bone, okay, could be lung, never. Then we look at the signal through the bone, and the signal in the background, we call it, or the average away from that. And it's essentially related to the difference in those signals. Okay, so a high contrast image would give us a big difference between those signals. A low contrast image, there'd be a very small difference between them. Okay? So this actual definition of contrast, because there is another definition, This is useful when we have quite small features in a large uniform background. Okay, so medical images are good examples of that. So, of course, what we measure in different imaging modalities, the signal is related to different physical quantities. Okay, so radiograph, an X-ray image, although ultimately it's the attenuation of the X-rays through this person's hand in this case, okay, we then convert that to an optical density. Okay, these days it would be digitally scanned. Okay, so this is an old, I guess, these days we probably have a digital imaging system, but let's think about it being optical density. So what we're doing, the way we can define the contrast here, we would look at the optical density at point A, so this would be our background, and then point B would be I guess the anatomy of interest, and that's how we would calculate the radiographic contrast. Okay, so this is a bit of a, I guess, probably not so important these days because of digital imaging, optical density. We just measure the signal directly with a digital imaging system. But it shows us how we can obtain contrast from any image. We just look at a region where, because of course this sort of region is, it's probably going to be just skin there, and then this will be bone. Okay. Now there is another type of contrast, or another definition for contrast, and this is known as modulation contrast. And this is useful where we have an image where bright and dark features take up similar fractions of the image. Okay, and this, in this case, it's the sort of the difference we're looking at here is the maximum signal and the minimum signal. That difference, okay, divided by the sum of the max and the min signal. So we'd have to search around our image for the maximum signal, search the image for the minimum signal, and then we can calculate this type of modulation contrast. Okay. Now the other thing is that there are, the actual final contrast that we see is made up of lots of stages. The imaging process can be made up of lots of different stages, and so there's a subject contrast, which is just due to the object we're trying to image. But there's also going to be some characteristics of the imaging detector which are going to influence what the image contrast that we actually end up getting. And then there's the display contrast. Okay, so this is what we then choose to display it on. So we can image the same object. So if you image someone's hand, the actual difference, the contrast you're going to get between soft tissue and bone, that's pretty much fixed. Okay, but then how you image it and display it is going to affect the final contrast that you might end up actually displaying and seeing. Okay, so that's important to remember as well. Okay, so the other important thing is so we looked at sampling, spatial sampling. We've looked at contrast, which tells us about the difference in intensities and the information we can get. But there's also the sharpness of an image, or unsharpness is. There's always an inherent unsharpness to an image, and this is because if we image a particular object, what we actually see is a convolution of that with some response function. Okay, and invariably, well, always this response function is going to be a blurring effect. Okay, so that's something we can't avoid. All we can do is design an imaging system that has the best response function possible for the application that we want to use it for. Okay. Now another consequence of this blurring is a reduction in intensity of the object. Okay. And of course, if we reduce the intensity, that goes back to a reduction in contrast. So this unsharpness and contrast are going to be linked. Okay. And that's essentially because as we blur the object, I guess it's, in a way we can think about it as conservation of energy. Okay. the signal, the energy in the object from the object, is just being spread out over a larger area. So the result is that, on average, in each pixel, that signal is going to reduce. Okay, so you can see this here that depending if we've got increasingly broader response functions, that as well as getting a blurring, okay, we're also getting a loss of contrast there, and it's becoming harder to actually see that object. Okay, so it's going to depend on the width of our response function, and that's what those numbers there are referring. These are the width of the response functions. Okay. So this is really only important once the size of the object is of the same order or smaller than that response function. Okay. If we have a large object, it's not going to be. We don't see any reduction in contrast. Okay. So it's really important when we're trying to see small details in an image. So we like to be able to quantify these effects. So one way of thinking about it is to think about, well, what would we get in our imaging system if we just imaged a point source, effectively, okay, or a point object. This would give us what we call the point spread function, okay, because if we have an infinitesimally small point source or object that we're trying to image, so for radiography it could be a pinhole, okay, which is actually quite hard thing to do, because it's also only an approximation. Then we would get a measure of the point spread function. Now, mathematically, we can think of this. We can think of the ideal scenario. What's the smallest sort of point object we can have? Well, it's the delta function. Okay, so we can sort of say, well, what happens if we were to? What would the image be if we got a delta function and we image that, and there's our response function? That would effectively give us our response function. Okay, and again, you might start to recognize a pattern here. This is actually a convolution. Okay, this mathematical representation of this integral is a convolution. So if we convolve a delta function with this point spread function, this gives us the sort of image function. So what we want, this is going to affect our ability to also distinguish close objects or objects between 2 points. Okay, if we have a very broad point spread function or image response function, it's going to make it harder to distinguish two close objects, okay, which are quite small. So the full width half maximum of our response function or point spread function determines the ability to, I'm going to use the word resolve, okay, because we're talking about resolution here, so the ability to resolve two small close objects, okay, which are discrete separate points. If our response function is too broad, then we're not going to be able to separate them. Now that measuring a point is actually, like I sort of alluded to it, is actually quite difficult. So there are other ways that we prefer to do it when we're carrying out quality assurance on imaging systems. One is to measure the line spread function. So for this we measure a narrow collimated slit. So we need to design some sort of collimator system that just allows a narrow, very thin slit beam. Okay, we can then orient this in two directions. Okay, in the two principal directions. That just allows us to analyze the unsharpness of the image in those two principal directions. And the line spread function, and mathematically we can just think of this as a whole, I guess, line of delta functions. Okay, and then what we get in our image would be this line spread function, which is blurred by a whole row of a line of point spread functions. Okay, but in this case we call it the line spread function. Another common way to do it, more practical way to do it, is to image an edge. Okay, so we design usually a block of lead or something that's highly attenuating, and we put that on the detector, we image it, and if it was a perfect imaging system, we would get a nice sharp edge. Okay, we don't. We get a blurring, and that blurring is, in this case, is known as the edge spread function. And the edge spread function and the line integral are actually related. Okay, mathematically, the edge spread function is actually the integral of the line spread function, and conversely, of course, the line spread function is the differential of the edge spread function. Okay, so we can measure the edge spread function, and it can allow us to determine the line spread function. Now, another important aspect is we're going to go back to the concept that an image is made up of lots of different spatial frequencies, and the imaging system is going to be it's going to differ in how it transfers information on each of those spatial frequencies into the final image. Okay, so what the modulation transfer function tries to do is to characterize this. Okay, so let's think about what's actually going on in an image. If we have a very sharp image, okay, with lots of detail, this actually corresponds to it having a lot of high spatial frequency information. Okay, so it's representing all the high spatial frequency information very well. Okay, if we get a blurring, then this is a reduction in that high frequency spatial signal. Okay, and we can measure this using typically a line pair phantom. I'll show an example of one of these in a minute. Okay, and then measuring the image signal as a function of the line pair separation. Okay, and the other thing to remember is that our imaging system is made up of a whole chain of separate contributions. So the individual components might have very good modulation transfer. So this C here is actually transferring high frequency information very well, but overall the system is going to be worse than that because these other components are actually not transferring the high frequency information as well. Okay, so the overall system modulation transfer function is always going to be worse, if you like, than the individual components. Okay. So this sort of shows if we image this. So this is this phantom would be in a material that would be embedded, highly absorbing and less absorbing. So typically it would be blocks of slices of lead and plastic. Okay, of in this case decreasing thicknesses. So the number of line pairs per millimeter is decreasing. Okay, sorry, the number of line pairs per unit length is increasing, and then we take a profile through, and you can see here. Okay, we get to a point where the signal intensity, which we can call modulation, if you like, decreases. Okay, when the line pairs become very dense. Okay, and so we can actually calculate this, and so this sort of gives us some information about we know that each of these locations corresponds to some spatial frequency information in terms of line pairs per millimeter. Okay, so we can see how well the system transfers high frequency information into our final image. Okay. So you can see for a long time we see no reduction in signal, and then suddenly it starts to fall off. So saying a bit about noise, I've already said no two images are ever the same. Okay, and that's because there are these random variations in the recorded signal from pixel to pixel. Okay, so the noise is proportional to the number of quanta that are involved in forming the recorded signal, and the ability to detect an object is going to depend on the contrast. Okay, so the difference in the inherent difference in the signals and the noise in the image. Okay, now this doesn't probably project too well. Okay, but this is 3 images of the same object. So you can see on the left one, definitely you can see the object there. Okay, the circle in the middle. but we're increasing the noise across as we go to the right there. Okay, and to the point where the noise is so significant here that we just can't, we lose that. It gets lost in the background noise. Okay, so noise is something we want to try and limit because it's going to also affect the contrast in our image, in the final image. Okay. Now, if the signal in our image is uncorrelated, so each pixel is effectively independent, okay, we can just use the variance to characterize the noise. So we just average, we work out the the mean and standard deviation of our pixel values. It doesn't have to be over the whole image. It can just be a region of interest. We did this in the tutorial last week, okay, and we'll have a look at it again tomorrow in tomorrow's tutorial. So this uncorrelated noise in the image is what we call white noise. So this is where we get all frequencies are equally represented. Okay, all spatial frequencies are equally represented. Okay. As I've already said, most imaging systems involve a cascade of different components. So this shows a simple X-ray detector. We've got some screen here, X-rays interacting, producing optical photons, which are then captured by some, as an old-fashioned image intensifier type system where it's a video camera or CCD camera probably these days. And we can see that at each point in the image, each stage in our image, we have a certain number of quanta. Okay, and what we find is that the limiting factor on an imaging system like this is the stage in the system which has the lowest number of quanta. Okay, and we call this the quantum sink because it's just where we lose a lot of information. It defines the noise in our image effectively. Okay, so the component of the imaging system with the least number of quanta will be the most significant contributor to the overall noise. Okay, so we want to try and limit the losses at every stage of our imaging system. Okay, this point 4 here is the capture of the optical photons. Okay, and the reason we lose a lot of signal here is because the optical photons that are produced are just thrown out in all directions, and then we have a very small solid angle. Okay, so to increase the number of quanta that we actually detect at this stage 4, we can either increase the area, okay, of this camera system, or we could have some alternative way that's right up against it and is going to capture more of those optical photons. Okay, so this is we can, rather than having a camera-based system here, we might have an array of photo detectors that convert the optical photons here into digital signal. Okay, but we can put that right up on the face of that, and that would reduce that quantum sink there that we've got at that stage of the detector. Okay, so when we're designing imaging systems, we have to think about this. We have to think about each stage. What's the physical process of the information transfer? What's the number of quanta involved? Because remember, the noise is proportional to the square root of the number of quanta. Okay, so that's why the lowest number of quanta is going to dominate that. Now, the important factor for us is actually it's not the absolute noise level, it's the relationship between the signal we're interested in and the noise in the image. Okay, so it's this signal to noise ratio, which we can calculate in an image if we take the mean value and divide it by the standard deviation. So our standard deviation is our measure of our noise, and the mean value is a measure of the signal. Okay. To get the other way we can do it is repeat a measurement multiple times. That will allow us to achieve if we had an ideal imaging system with no noise whatsoever, we would get the same pixel value every time. Okay, so the variations in the individual pixels when we repeat the same imaging process give us information on the signal-to-noise ratio. But that's often not practical, so we normally just acquire it. We might only have available a single image, so in that case we can take a single image and look at the mean invariance over a region of interest. But this does assume pixels are uncorrelated. If there's any correlations between pixels, that this way of measuring the signal-to-noise ratio is going to break down. An alternative way of doing it is to look at a region of interest and then have another region of interest, which is the background. Okay, so what we do is we just, in this case, we look at the mean value in region B, the background, and our region of interest, mean value A, and then we divide it by this standard deviation of the background. Okay, that's another way of the signal-to-noise ratio. And we can sort of visualize this. These are our two signals, and they're Gaussian, remember? So we've got a Gaussian distribution, and the separation of these, the contrast in the image is going to depend on the separation of them and the width of the distribution of the pixel intensities, okay, in those regions. Is that the last slide? No. Now, another quantity that's useful for us is how good the system is in transferring information that's input into it into the final image. We can characterize this as the detective quantum efficiency. And for that, we need to look at we take the signal-to-noise ratio at the final signal-to-noise ratio, and divide it by the signal-to-noise ratio going into the system. Okay, and that ratio we call the detective quantum efficiency. So this is useful for those which most imaging systems are sort of cascaded imaging systems. So this sort of highlights, and we'll have a look at this. We can do some imaging experiments tomorrow where we're going to investigate this effect of contrast and noise on the visibility of features in an image. So we've got, you can see it in the top case there, we've got some amount of noise on the image, and then our signal. So what we want is that the signal is easily distinguishable from the background, including the noise there. Okay, so this would be considered to have a low signal-to-noise ratio, so this would be difficult to see in an image. These are just 1D profiles through an image, of course. This would be considered to be high signal-to-noise ratio. Okay, it's quite obvious that we've got a separate signal there. Again, this time you can see that although this signal is reduced compared to that, okay, we've got reduced noise. So this is going back to that point I made about it's not the absolute differences in the signals and the noise. It's actually the relationship between the noise in the image, or the signal in this case, and the signal of interest. Okay, and in this case, you can see it would be difficult to distinguish it, but because we've got a larger object, it means that larger objects mean that we are able to visualize in situations of larger, more significant noise. Okay, so object size has an importance as well. And sort of visually, we can see that just different levels of noise. This is something we're going to do tomorrow. Okay, we're going to create some images that look something like this, and we can vary the noise, and we can just see that here we've got different size objects with different signal intensities for each object, and also different levels of noise. And you can see how it affects our ability to visualize and see those objects in the image. Okay. I think this has died. So in terms of spatial frequency information, we can get this from a line pair phantom. So that's what this is. Okay. So we have these are most imaging departments would have to have these sorts of phantoms, and they've got each of these has different what we call line pairs per millimeter. Okay, so the more line pairs per millimeter, if we're able to distinguish that, I guess the better the resolution of the system. So these are good at quantifying the spatial frequency that we can see, and we do this if we repeat this routinely. We see any degradation in the maximum spatial frequency we can see, then we need to, there's possibly something gone wrong with our imaging system. These are just some practical things that when we're measuring that edge response function, if the pixel size is of a similar size to the resolution limit, then we can get, it sort of makes sense to, the object, you see the edge there we're trying to image, and these are the pixels in our detector, we just orient the edge so that it's not aligned with the pixels there. That allows us to visualize effectively get a better sampling interval, okay? Because the sampling interval is given by this delta x sine theta, okay? So that's something, a little trick we can do to image the edges and obtain the edge response function where the resolution, we're close to the resolution limit in pixel size. So just this just final two slides just summarizes. This is, for what good spatial resolution means. It means we have a narrow point spread function which has a small full width half maximum, which means we can visualize high density information or high resolution information with large numbers of line pairs per millimeter. And this corresponds to a wide, broad modulation transfer function because we're getting a good representation of the high frequency information in the image. And poor spatial resolution, we're going to end up with a wide point spread function. So if we image a point source, we're going to have a very blurred image, a large full width half maximum of that. The number of line pairs per millimeter that we're able to visualize is going to be quite small, and this manifests itself as a narrow modulation transfer function. So the system is not being very efficient at transferring the high frequency information there. We're losing that. Okay, so these are the sort of, I guess, four sort of concepts we need to understand when we're thinking about the image quality and what's affecting the image quality in a system. So I think that was the last slide. Okay. So has anybody got any questions on any of that? Yep.